In my earlier video, I had discussed about inner product and norm on a vector space. I had said inner product actually be function to define dot product. Actually, geometrically, inner product is defined to define the angle of vectors and norm defined to define length of vectors, and metric space will define to define distance of vectors. Actually, inner product be a function from V cross V to real number, because inner product always indicate the dot product. Today's goal of this lecture is positive definite matrix. I had seen in my earlier video what is the positive definite matrix with example. I had seen relation of positive definite matrix with inner product, some theorems about inner product and positive definite matrix, how they are related both. Today I will see this topic elaborately. Also I will see one linear transformation between inner product and positive definite matrix. This is our first goal, because this part is very important for any competitive exam and higher study. Our next goal, I had defined norm on a vector space with example and properties. Today I will see different type of norm which is induced by inner product, because inner product is means dot product and dot norm is always implied length of the vector. So norm always induced by inner product. I will say couple of example of norm which is induced by, sorry, here not norm, here inner product. Okay, this is our goal of this lecture, and this example norm induced by inner product, this example is very important for any competitive exam, also for higher study, also used for understanding metric space in better way. So I will highly recommend you, at first please see today's video with pay attention, because this topic is very interesting and very important. Okay, now let's come back our original discussion. Let's see relationship between inner product and linear transformation. The relationship is, consider two vectors. Now apply M as a linear transformation, and this linear transformation is injective. Then after transformation, this vector can be scaled or angle can be changed. Consider this type after linear transformation. Then inner product xy would be equal to inner product mx comma my. Now by the property of inner product, this would be my transpose mx, which is equal to y transpose m transpose mx. Okay, since I have considered M is injective linear transformation, that means this rank would be full rank. Consider this is equal to A matrix which times x. Okay, this is actually the relationship between inner product and linear transformation. That means inner product xy under the matrix A would be equal to, we can write this as also inner product x with x under the matrix A, which is would be, since from this x transpose Ax And since this is inner product, then that means this is always strictly greater than 0. X transpose Ax greater than 0, that imply A is a positive definite matrix. Okay? Which has a quadratic form. Are you getting the relationship between inner product and linear transformation? Now let's see actual definition of positive quadratic form. Suppose ABRn, which is a symmetric matrix, then we can define a homogeneous quadratic polynomial in n variable using the function qx equal to x transpose ax, where x transpose ax means this type of polynomial. Here I have considered R2. Okay, this is the quadratic polynomial, where this quadratic polynomial be a function from Rn to R. This is because this is the scalar. Then the function q is defined as quadratic form on Rn. Are you getting the definition? OL. Now I will discuss this transformation elaborately. Consider inner product VWB symmetric bilinear positive definite. Then construct an inner product where V equal to the vector x1, x2 up xn and W equal to the vector y1, y2, yn. If we consider the standard inner product, then inner product V with W would be x1 y1 plus x2 y2 up to xn yn. But if we scale this vector by a1, a2, an, then this would be a1 x1 y1 plus a2 x2 y2 up to an xn yn. And we can write it as x1 to xn with the matrix a1 0 0 0 a2 0 0 up to 0 0 an with the column vector y1 y2 up to yn. Are you getting? OL. If we write the matrix as A, then this is actually equal to V transpose AW. Okay? Here, this is diagonal matrix. Try to construct an inner product V with W under the matrix A such that V transpose AW where A, EB, n cross n matrix. Okay? Consider the vector space V. Here, consider the basis element R, V1, V2, Vn. Therefore, we can write the vector V as a1 V1 plus a2 V2 up to an Vn. Also, the vector W we can write as B1 V1 plus B2 V2 up to Bn Vn. Okay? Therefore, inner product V with W is equal to a1 V1 plus a2 V2 plus an Vn, comma B1 V1 plus B2 V2 up to Bn Vn. Okay? And by the property of linearity, we can write it as a1 times V1 comma B1 V1 plus B2 V2 up to Bn Vn. Okay? Plus a2 comma V2 comma B1 V1 plus B2 V2 up to Bn Vn, okay, plus An times Vn with B1 V1 plus B2 V2 plus up to Bn Vn. If we apply again bilinear form, then this would be A1 times B1 inner product V1 with V1 plus A1 times B2 inner product V1 with V2 up to A1 Bn inner product V1 with Vn plus A2 B1 inner product V2 with V1 plus A2 B2 inner product V2 with V2 up to A2 Bn inner product V2 with Vn, and this would be continue. Then last term would be An B1 inner product Vn with V1 plus An B2 inner product Vn with V2 up to An Bn inner product Vn would be Vn. Okay, therefore inner product V with W, we can write it as summation ij 1 to n aibj with vi comma vj. Okay, so we can write inner product of any two vector as inner product of basis vector. Are you getting? Well, therefore we can write it as A1 comma A2 up to An. Then the matrix would be inner product V1 comma V1, inner product V1 comma V2 up to inner product V1 comma Vn, then inner product V2 comma V1, inner product V2 comma V2 up to inner product V2 comma Vn. Now continue this process. Then this would be n term would be inner product Vn comma V1, Vn comma V2 up to Vn comma Vn, and this is n cross n matrix with B1 B2 up to Bn vector. Are you getting? And notice this, if we consider this matrix as A, then A is n cross n matrix. Therefore here inner product V with W is written as V transpose AW, where A is n cross n matrix. Therefore I have got inner product V comma W, we can write it as V transpose AW, where A is B n cross n matrix. Therefore for every inner product there exists always B n cross n matrix with respect to basis. Therefore with respect to different bases of a vector space, I will get different type of symmetric positive definite matrix in the vector space. Have you understood? Oh well. As for example, find the matrix A that represent the usual inner product on R2 relative to the basis V1 equal to 3, 5, V2 equal to 1, 7 of R2. Here notice inner product V1 with V1 equal to 9 plus 25, which is equal to 34. Inner product V1 with V2 is equal to 3 plus 35, which is equal to 38. Inner product V2 with V1 is equal to 3 plus 35, which is equal to so 38, and inner product V2 comma V2 would be 1 plus 49, which is equal to 50. Therefore, the matrix A equal to, notice, at first would be V1 with V1 inner product, then V1 with V2, then V2 with V1, then V2 with V2, and this is actually nothing but 34, 38, 38, 50. Are you getting? OL. And these matrices, notice, this matrix is symmetric matrix. Therefore, with respect to this basis of R2, I will get this matrix which is symmetric and positive definite. Okay, discuss our second goal. Norm induces by inner product. Inner product and norms both are closely related. We all of us know, because any inner product always induces a norm, because norm means square root of inner product with itself. In a natural way, we can compute length of vectors using inner product. However, not every norm is induced by inner product, which I will discuss in my next video. There exist many norms which cannot produce inner product. So every inner product produces a norm, but every norm does not always imply it produces inner product. That means inner product always induces a norm. The theorem is, let V be an inner product space within the inner product, then the function which is denoted as norm from V to R, which is defined by inner product square root of V with itself, this is always be norm. If we want to prove this is very easy type proof. This will satisfy all properties of norm. First, norm of V equal to 0 imply square root of inner product V with itself equal to 0. That imply, obviously, inner product V with itself equal to 0, and inner product V with itself equal to 0 imply by the property of inner product, this imply V equal to 0. And if V not equal to 0, then inner product V with itself by the property of inner product, this is obviously greater than 0. And that will imply obviously square root of inner product V with itself greater than 0. And these imply norm V greater than 0. And norm of CV equal to square root of inner product CV with CV. This is equal to square root of C times C with inner product V with itself. And this means square root of C square times inner product V with itself. This is equal to mod C times inner product V with itself. Okay, that means multiplication property also satisfied here. And norm V plus W equal to square root of inner product V plus W with V plus W. By distributive property, this is equal to square root of inner product V with itself plus inner product V with W plus inner product W with V plus inner product W with W. This is equal to square root of inner product V with itself plus 2 inner product V with W plus W with itself. Now square both sides, then this would be V with itself plus 2 inner product V with W plus W with itself. And V with itself means, we all of us know this is norm V square, and this is mean norm W square plus 2 inner product V with W. Okay, and there exists an inequality inner product V with W less than equal to norm V times norm W. That means from this expression we can tell this is less than equal to norm V plus norm W. Therefore, from this expression we can tell this is less than equal to norm V plus norm W whole square. Okay? That means all property of norm has satisfied. That means all inner product induces a norm. Are you getting? This is very important. But there exist many norms which does not satisfy all properties of inner product. So, converse not true. That means inner product induces norm and norm induces metric space. Then let's see some example. What is the norm induces by standard inner product Cn? Euclidean norm. Which is norm V, which is equal to actually square root of I equal to 1 to n Vi, absolute value of Vi whole square. In Cn there exists other norm also, but this norm induced by inner product. Okay? And I will see in my next video in Cn different type of norm. Because inner product always induced a norm, but norm does not imply it is always induced by inner product. Okay? Let's see some more example also. What is the norm induced by standard inner product on CAB? I had seen in my earlier video. This is the inner product in CAB. Then in CAB the norm would be square root of integration a to b fx whole square dx. Then next question, what is the norm induced by standard inner product n cross n matrix? Here I had seen inner product here defined as inner product AB is trace of A transpose B. Okay? So the norm would be just square root of trace of A transpose A. This is it's actually equal to square root of summation I equal to 1 to n and summation j equal to 1 to n aij whole square. Today I will stop here. In my next video, I will discuss different type of norms in RNCN. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.